Imagine trying to find one specific needle in a giant, three-dimensional haystack. That's pretty much the challenge doctors are up against when they're searching for tiny anomalies in complex 3D medical scans. So today, we're going to dive into how AI is learning to become a kind of expert search engine for the human body. And here's the heart of the problem. Every single day, the amount of medical imaging data just skyrockets. Now, you'd think all this information would be fantastic, right? And it is. But it's also leading to massive workloads and serious burnout for radiologists, the experts we count on to read these scans. So that brings us to the big question. We have these enormous archives of clinical history, all this valuable information just locked away in image files. How do we build a system smart enough to unlock all that data and turn it into a powerful, searchable tool that actually helps doctors make better, faster decisions? All right, here's how we're going to break it all down. First, we'll dig into the data overload problem that radiologists are dealing with. Then, we'll get into why searching in 3D is so uniquely tricky. After that, we'll introduce a new standardized test for AI called the 3D-MIR benchmark, see how different AI models stacked up, and finally, we'll talk about what we learned from it all. Okay, so let's start with the human element in all of this, the incredible data overload that radiologists are facing every single day. It's a perfect example of how more isn't always better, and it has some very real consequences. And this is really two sides of the same coin. On the one hand, you've got this immense pressure on doctors because of these constantly growing workloads. But on the other hand, you've got this amazing, untapped resource, all of that historical data just sitting in databases that could totally help with clinical decisions, if only we had the right tools to access it. All right, let's pivot to the technical side of things, because this is where it gets really interesting. Searching through a 3D CT scan is a fundamentally different beast than the simple 2D image searches we do on our phones every day. It's not even in the same ballpark. And this analogy just nails it. A normal 2D search is like finding a photo of an orange. The whole thing's right there in one flat image. But searching a 3D CT scan, that's like someone handing you hundreds of paper-thin, transparent slices of the orange and asking you to find a tiny blemish somewhere deep inside. If you only look slice by slice, you're going to miss the big picture, the full three-dimensional context. So, if you want to build better search tools, you first need a way to measure them, right? You need to know what good even looks like. That's what led to the 3D-MIR benchmark. Think of it as a standardized obstacle course built specifically to test how well different AIs can find their way through this complicated 3D world. And listen, this isn't just any old dataset. It's the first public benchmark of its kind, designed from the ground up for 3D medical image search. It zeroes in on CT scans of 4 really important organs and is built to see if an AI can find not just similar-looking images, but actual medically relevant information inside them. Building this thing was a super cool 3-step process. First, an AI goes in and essentially carves out a specific organ from a full-body CT scan. Then, the system zooms in on that organ and identifies every single lesion, giving each one its own ID. And finally, it analyzes the nitty-gritty details of those lesions, how many there are, how big they are, creating this incredibly rich, searchable database. Okay, so the obstacle course is built. Now it's time for the main event, the Great Search-Off. Researchers took several different AI search strategies and put them head-to-head to see which one was the best at finding that needle in the 3D haystack. First up to the plate is the slice-based method. This is that approach we talked about with the orange. It looks at every single 2D slice of a scan one by one, finds similar slices from all across the database, and then kind of pieces all that information together to figure out which 3D scans are the most similar overall. The next contender uses a completely different strategy, volume-based retrieval. Instead of looking at individual slices, this method takes all the information from all the slices and squishes it down into a single unique fingerprint that represents the entire 3D organ. Then it just compares those fingerprints to find a match. And finally, we have the most futuristic approach of all, multimodal retrieval. This is where a doctor can literally just type a question in plain English, like, "Show me a liver with 2 tumors." The AI has to be smart enough to understand the text and then go find the 3D images that actually match that description. Pretty amazing. So, the big competition is over. The tests have been run. What did we actually learn? Let's get to the verdict and talk about what this means for the future. Well, the biggest takeaway might actually be a little bit of a surprise. It turns out there's no single magic bullet. No one AI search method was the best at everything. The right tool for the job really depends on what you're asking. Let's break that down. The volume-based method, the one that creates that single fingerprint, was great for big, broad questions, like, is there a lesion in this organ at all? But the slice-based method was way better when you needed the fine-grained details, like exactly how many lesions are there and what size are they. And to add another layer of complexity, the researchers found that the best method also changes depending on the organ you're looking at. As the paper itself says, no single method is the best across all organ types. Which makes sense, right? The anatomy of a lung is completely different from a pancreas, and that affects which search strategy works best. So at the end of the day, this work wasn't really about finding a single winner. It was about laying a completely new foundation. By creating this benchmark and testing these different methods, these researchers have paved the way for turning these massive, overwhelming data archives into truly intelligent tools that can help doctors make better decisions. And this leaves us with a really fascinating thought for the future. As this tech gets better and better, you can imagine a doctor being able to ask the system to pull up thousands of similar past cases to help with a tough diagnosis. Which leads to the question, could a smart AI search engine one day become a doctor's most powerful tool for getting a second opinion?